Hi, in this video, we want to take a look at how to integrate the bnlearn package with other R packages, specifically the ones for graphical models. So in R, there are a ton of specialized packages for dealing with graphical models. Unfortunately, each of them have different structures, different types of objects. All of them have strengths and weaknesses. All of them bring something to the table. If we want to be able to fully leverage everything in our model, we need to be able to pull in functions from other packages freely. All right, so something that's going to be very important about this is we need to be able to go from bnlearn to another package to bnlearn back and forth. So if I have a model and it's stored in a format for one package, I want to be able to go back and forth between other package formats. Unfortunately, this is an additional step. This is something that we're kind of stuck doing, but if we're going to be serious about working with graphical models in R, we need to be able to do this. All right, here is a good rule of thumb. If you ever get stuck and are having trouble crossing between packages, convert it to the adjacency matrix, and then convert the adjacency matrix to the type of model that, or the stored object class that you want. Or extract all the edges and arcs and then convert that over. So if you don't know what to do, you get stuck, go the adjacency matrix route for conversion. That's an intermediate step, or pull out the edges and nodes and then convert that way. Honestly, if there's a function that does it for us automatically, of course, that's the one we're going to want to use. But if you don't know what to do, the adjacency matrix way works, but that's not going to work very well for big data unless you store it as a sparse matrix, and then the receiving package can handle sparse matrices. So in that situation, we'd want to work with the edges and the arcs directly. Okay, so let's start getting more specific and start working through some examples. Much of the code that I'm going to be going through was copied and pasted or modified from bnlearn.com. And so this is the website for the bnlearn package. It's a lot of good resources, a lot of good information. If you want to dig in deeper, here are two books to look at. The first one is downloadable through the Springer Link repository of books. If you're a UCF student, you can click on it and through the library's webpage and go ahead and get that and get going and work on it. The other book is a CRC publisher book, and it's a good book. I have both of these on my shelves. I have the hardbound version of both of them, and I've worked through all the examples on the website and both of these books. There's good information in all three of them. There is substantial overlap if you're going to work through them all, but since I professionally use Bayesian networks, I definitely need the information contained in there. All right, so the first package that we're going to look at is the deal package. So what's the deal? All right, this is one of the oldest R packages for structure and parameter learning. It generally supports conditional linear Gaussian networks. So what this is saying is that basically between nodes we have linear regression. That's really what that says. And when I say linear regression, that means that we have numeric variables going on. So this isn't going to support discrete data structures for graphical models. It implements a single learning option of hill climber, which is a good one to go with. All right, so one of the things we want to be able to do is we want to be able to go from bnlearn to the deal package to bnlearn. Each package has their own structure for storing a model, and we need to be able to bounce back and forth. So let's go ahead and take a look. So here is my code. So first and foremost, I pull in the bnlearn package. And we can see that we've got the potential for package confusion coming up. We need to be aware of that if I want to use a sigma function down the road. All right, the data, for all the examples here, I'm going to use the alarm data set. And for my bnlearn models, I'm going to be using the hill climber algorithm within bnlearn. All right, so the method of working with this in for when I do deal is that I'm going to take my model, I'm going to extract the character string that tells me what my model is, and then I use that to convert. And that way I can go back and forth very easily. These both packages use the same character string format, and so everything's like really easy. Like once I grab the character strings, I've got the equivalent information from either way. I can pass it to deal, I can pass it to bnlearn, we're all good. So what we're going to do, we're going to take the model string from our bnlearn model. I call it model string alarm. Now, what I'm going to do, and this is because of the deal package, there is a topological ordering in the that's inherent to every single Bayesian model. And so basically you can think of it as if a node has no arrows pointing into it, it's going to be higher up than, or so if I have node, and there's an arrow between them pointed in that direction, this one comes first, this one comes second. And so there's a partial ordering that we can apply to the entire data set columns based off of any model that we have that's directed. So what the deal package wants, the deal package wants the data in that order. And that's a very natural order if we already have our model established. So what I'm doing here is I'm getting that topological ordering, and you don't need to know topology to understand what's going on. Just nod your head at it. We don't need open sets, and we don't need to do any topology nonsense. Once I get the partial ordering, I'm going to rearrange the columns of my data set. Now that I have my data in that order, I can pass it to the deal network, the deal network function, and it will go ahead and make a model for me. So here I have deal alarm. Now here, I don't quite have, so here's my model string. And here is the network. And so I pass them to as.network. And then, so right now, deal alarm is a model, and it's stored in the format of the deal package. That's how it's stored right now. Now, there's going to be a lot of things in it. It's a complicated thing. What I'm going to do, just to show you that I got the right output, I'm going to look at the model string pulled from here. So when I do this part, I am extracting the model string from the deal model. And here it is. It's beautiful. It's beautiful, beautiful. So how we read this is that this hist variable has no arrows pointed into it. Same thing with HRVP, PAP, don't have any pointed into them. Now, if I look down here, notice what I've got going on. I've got the VMCH variable, and I've got VTub, and I've got DISC. These two variables have arrows pointed into this variable, and that's how we read this. The MVS variable has VMCH pointed into it, and that's how we can understand what's going on. Now, it's possible to rearrange these parts inside. We can rearrange the brackets themselves and get the same model. It actually doesn't matter what the order is, but in general, we want the ones that are like earlier in the topological ordering to be first, and the ones later in the topological ordering to be last. And you'll know, if you look through here, you'll notice that in this entire model, if you were to count through the entire one, MVS does not point into any other models if I was to go through and check it. Now, if I scroll down a little bit, here's the model string for the bnlearn. So this model string here, this is for the model when it's stored in the deal package format. This is the model string when it's stored in the bnlearn format. And so if we go through and we check bit by bit by bit, we'll see that these are the same. So because I have the same, I know I have the same type, I have the same model, and then this enables, or this confirms that we can go back and forth between the two packages. So if I convert from one to the other, I'm not losing anything, and I'm not picking up anything that I don't want. All right, so that was going from deal to bnlearn. Now that was bnlearn to deal. Now we want to go deal to bnlearn. All right, well, it's the same thing. What I do is I take a model string. So here, I take the model string from the deal model, and then I just pass it to the model to network format. So here is my model in the deal package. This is the character string that we just looked at a moment ago that tells me the relationship between all my variables. All right, so I have that character string. Now, if I pass it to the model to network, then I get the model. So the output, the final output is going to be a bnlearn model. Started with a model stored in the deal format. I end with a model stored in the bnlearn format. And so this enables me to use all the strengths and features and advantages of the bnlearn package if that's what I want, or I can use all the strengths and advantages and features of the deal package if that's what I want. I can go back and forth. All right, now we want to take a look at the pcalg package. So this is a versatile package. It implements a score-based algorithms with a greedy equivalent search and constraint-based algorithms, such as the PC. And it can handle discrete data sets as well as continuous data sets. So bnlearn can handle continuous, discrete, and hybrid, a mixture of the two. The deal package can only handle the continuous, and when we say continuous, we mean Gaussian. So anytime it's strictly numeric data, it's doing Gaussian every single time for the packages in R. Theoretically, any continuous distributions could be used, but the actual implementation, what's been achieved, what's available to us without having to build something ourselves, is always Gaussian. All right, so something about the pcalg package is that we need to specify our independence test to be able to build a model. And so you'll notice that we have a test for deseparation. We have binary tests. We have discrete. So when it's not when I have data that's not binary and it's discrete, this is the one I want to use. And here, this is when I have Gaussian data. So this is for continuous. Now, something that's kind of wonky about this package is that if I have discrete data, it has to be stored as 0, 1, 2, 3 up to n-1. So from 0, so if I have 5 levels, it goes 0, 1, 2, 3, 4. So it's always going to be 1 less, 0 to 1 less. And when I pass it to the PC algorithm. And so we need to do a little bit of work to prep our data set. All right, so first thing I did was I used this function, this sapply call, to figure out how many levels are there in each variable in the alarm data set. And I store that as a vector. Now, so that tells me how, so the system wants to know how many levels are there for each individual column. What we do over here is we use as an integer to convert the factors in the alarm data set to integers. So under the hood, anytime that R is dealing with a factor, under the hood, it's actually stored as an integer. Like if there's 5 levels, it's going to be 1, 2, 3, 4, 5. and it's going to be in the order that you specify. If you don't specify an order, it's automatically assumed to be dictionary order, alphabetical order. Okay, so as integer almost gets us there. You know, if I have 5 levels, that's going to give me 1 to 5. But remember, I need 0 on it, so I'll go ahead and I subtract 1. So if I have categorical data and I want to start building a model with this package, one thing I have to do is it can't be a character string, it has to be a factor. And then after I have it as a factor, I have to have it as an integer. And not only do I have to have an integer, it has to start at 0. It's not that difficult, but it's something, it's a step along the way. And so after I'm all done, it's going to be an additional step to be able to interpret what's going on because I have everything in integer format. So after I'm all done, I have to go from, oh, well, I see that it predicts a number 3 for this variable. What's number 3 on this variable? I have to convert back. Additional steps, kind of a pain in the neck, but we could potentially do it. All right, so something about how this package operates is that it likes to have what it calls its sufficient statistics contained in a list. And the binary and the discrete and the Gaussian conditional independence tests all have slightly different parameters to put in. So you need to go through and make sure that you have it in the right order. And you want to name the items in the list. You notice I've got DM, in levels, and adapt DF put in here. And so now you'll see that I pass the list of sufficient statistics to the PC algorithm. I've got discrete data, so I'm using the discrete conditional independence test. I put alpha at 0.01. That's what the help documentation usually use. A lot of times the authors have good intuition on what a good default value is. So I went ahead and went with that. And then the labels are the column names. And I pass all of that to the PC algorithm. So what this does, this goes through and this fits a model for us. Now let's go ahead and plot it to see what it looks like. And all right, through my videos, time and time again, I complain about R Markdown passing to Word and making like the good visualizations look bad. No, this is how it looks in R. It's not great. I mean, if you really want to stare at hard, you can figure it out. You can mess with the parameters, but this really is not the best version of plotting a graphical network. So I wouldn't recommend using it, but it's available to us if we choose to use it. Now, if I want to convert that over to the bnlearn package, so here I have a model that's in the pcalg package format. I need to convert that to the bnlearn package format, and I just use as bn. So it says as a Bayesian network, convert this over, and it goes through and it does this for us. It's nice, very beautiful. I'm getting emotional about this. All right, so when we import a Bayesian network into bn.fit objects, it's not going to, some things are not going to be supported, so you have to be ready for that. In general, when you're doing something in the bnlearn package, it's going to check for cycles to make sure that you're not making a mistake. If you don't want to check cycles, you have to set check cycles equal to false. So something that you can do that this can speed up your conversion. Like if I know I don't have cycles and I don't want to check because I would just slow down the system, I can do check.cycles equals false, and that would help me out. Also, maybe I want a cycle in there, and I want R to just go ahead and give me the model, and I'm not going to use any features that will break with cycles in them. And so in that situation, what I want to do also, I would set check.cycles to false. All right, the next one that we're going to take a look at is the graph package. Now, we've already taken a look at this when we looked at our graph viz. So if you remember to use our graph viz, what we did, and that's the one we use for visualizations. For our graph viz, we converted our bnlearn package to a graph package format, then used our graph viz. So, you know, an additional middleman step in there. So there's a lot of good features in this package. It's one of the most popular ones to work with. It has a lot of features, a lot of supports to it. You can really leverage some stuff out of your models. All right, there are two major ways that the graph package stores a model: the graph nel object and the graph am object. All right, so the graph am objects use adjacency matrices. So what's going on is that it stores a matrix with a bunch of zeros and ones on it. 0 if there's no connection, 1 if there is. That's it. Now, that's a good format. That's a good general format, but that can get very large for large data. And it's unwieldy to look at for humans because it will be both wide and long. If I need to, especially in the big data situation, then like when I have a lot of predictor variables, the graph nel objects are better to work with. For graph nel objects, what we do, we have a list, and the list specifies the connections between different nodes. All right, and so, yeah, in the adjacency matrix format, there's a lot of, if you're really big on the graph theory and you want to start leveraging graph theory aspects and like using the eigenvalues and things like that to study your model, you're going to want to use adjacency matrix frequently. If you do like a proof-based graph theory course, you're going to be using adjacency matrices up, down, left, and right, and that makes it. And that's where you can really leverage that format. For us, for our purpose is really to make like predictive models, to do machine learning, and the adjacency matrix is not as important to us. All right, so we want to export a bnlearn model to the graph format. So the situation is I have a model stored in the bnlearn format, and I want to use some feature of the graph package. So first I have to convert my model to how the graph package stores it. And fortunately, this one is super easy. We just use as whatever format we want. So if I want graph nel, I do as.graph nel. If I want graph am, I use as.graph am. That's it. Easy peasy lemon squeezy. So what we do, we take our bnlearn model and I pass it to as graph nel. Now you'll notice that the bnlearn package is the one that's supporting this one. That's nice. The bnlearn package does a good job of enabling us to go between packages. And if I have a model and I want it to be stored in the graph package format using adjacency matrices, I just use as.graph am. Easy peasy lemon squeezy. And so previously that was the output from a hill climber algorithm. If I have a bn fit, then it works out the same. So the difference between these, this example is showing what happens when I don't actually, when I have the structure of the model, but I don't have the fitted probability tables worked out. I haven't actually fit the parameters of the model. I just have the edges. I have the relationship between the variables. This part of the example is when I don't have parameters, I don't have probability tables worked out. This example down here with bn fit, this is a situation where I have the relationship between the variables and we have the parameters worked out, we have the probability tables worked out. And so it's the same thing from our point of view. We don't care about the difference. It's under the hood is different. All right, now we want to take a look at taking something that's in the graph format and then convert it to a bnlearn object. So here I have a GraphNL model, and I want to convert it to a bn. So the model is stored in the GraphNL, or excuse me, the model is stored in the graph package format. I want to convert it to a bnlearn format for being saved. And we just use as.bn. Easy peasy lemon squeezy. And when I do that, you know, it just makes a model for me. It gives me the character string, and I can easily move about the bn package at this point. Same thing if it's stored in the adjacency matrix format. And remember that almost always in the bnlearn package, it's going to check to see if there's a cycle in there. So the bnlearn package, its primary goal is to have directed acyclic graphs, so no cycles at all. So it's going to be checking to make sure we don't make a mistake. How do we avoid these problems? We just set cycle or check cycle to false, and won't be an issue. So for this example, I've gone through and I've made a permutation matrix that is just a cycle of three nodes. It just goes from 1 node to 2 node to 3 node and back to 1. And so then here is a permutation matrix that I built out. Here in the graph package, I am building the model. And I call it cyclic because it's a cyclic graph. And then here, if I try to run as.bn on cyclic, it's going to give me an error. And my R Markdown object or my R Markdown document isn't going to render, it's not going to build. So I went ahead and put it in the try because it goes, hey, there's an error, there's a mistake. I can't have directed cycles unless I say it's okay. So here, what I do, I go ahead and I say, don't worry about cycles, just accept it as is. So the situations I want to do this in is when I want cycles, I want to include models with cycles, or I know I don't have cycles and I don't want the system to waste time checking. That second one, if I have big data, that can save me some time. And so here it spits out the model for us. Next one is the iGraph package. This one is used in a lot of different places. When I've taken a look at it, this is good for supporting models after they've been built, but not actually building the models, unless you know the structure already. But this really does offer a lot of tools and a lot of utility after you have the model learned. Now, I had trouble with the help code on this. If you look at the website, bnlearn.com, I couldn't get the help documentation to work. So I got stuck, didn't know what to do. So what I chose to do to work with this, I converted my bnlearn model to an adjacency matrix, and then I converted the adjacency matrix to an iGraph model. So when you get stuck, if you don't know what to do, convert your model. So when you're trying to bounce between packages, convert your model to adjacency matrix, convert adjacency matrix to the package format you want. So here, I'm getting the adjacency matrix of my bnlearn model, and then I'm passing it to the iGraph function for converting adjacency matrices to models. Like once you know how, it's pretty easy, but I was struggling with this pretty fiercely today. And then we can go ahead and plot it. And once again, that's not a very good looking plot. It didn't look good in R, it doesn't look good in R Markdown, all the same. I would use rGraphViz if I wanted to present this model in a presentation. This statement I found to be incorrect, but I went ahead and included it. That is this basically saying that under the hood, when I have undirected arcs, they become like two directed arcs in opposite directions. And you'll notice that here we don't have any arrows going on. Now we want to take a look at the situation where my model is stored in an iGraph format, and I want to convert that over to the bnlearn format of models. Okay, so how I chose to do this was I have an iGraph stored model. I convert it to an adjacency matrix, and then what I have to do is I create a graph without any edges, without any arcs. All I have are the nodes. In bnlearn, the empty graph command gives me a graph with nodes but no edges, no arcs. So here at this point, this model is a bunch of variables that have no connections to any other variable. So I have, this model says everything's independent. Then what we do is I say, hey, the adjacency matrix of this new model should be the adjacency matrix I built up here. And then that automatically builds what we want. And so then the bnlearn package does some rearranging because each package likes their adjacency matrices a little bit different. And so this part is just saying, hey, we moved it around. The adjacency matrix is a little bit different. Equivalent up to permutation, the same matrices, but they are permuted versions of each other. And so then we end up getting the model that we wanted in the first place. And once again, we want to tell it to not check cycles if we don't want to check cycles. All right, the grain package is another one. It supports discrete Bayesian networks, and it uses things in the grain class. And it stores things with a list of conditional probability tables. I found the conditional probability tables in this to be very, like honestly, easier to work with. And so if I want to figure out specific probabilities, this is probably a good package to use. Something that is different about this from bnlearn is the relationship for when we have, if I don't have data for particular instances, it's going to fill in stuff using the marginal probabilities for us. And so the major difference between converting on this one is that grain will go ahead and fill in stuff when I don't have it already there, or the bnlearn package won't fill in with conditional probabilities until it's absolutely needed. It's more lazy in that aspect. All right, so if I have a Bayesian network from the bnlearn package and I want to create a grain, a model stored in the grain format, I just use as.grain. All right, I know that's surprising. And you'll notice that right off the bat, I get this warning that we have not a number, conditional probabilities in a particular variable. And so what it does, it goes ahead and replaces, it fills in that information with the uniform distribution. So if I had 3 levels, it's going to say 1/3, 1/3, 1/3, like that. And it does the same for this one. It does the same for this. And so here, here's the actual model. And only discrete networks can be exported because that's the only thing that grain can handle. Yeah, so whenever we would be entering not a number into the grain package format, it's going to go ahead and find something to put in, usually the uniform values. All right, so now we're in the situation where I have a model stored in the grain format, so it's a grain object, and I want to convert it to the bnlearn package format. And so here, what we're doing is I'm using bnlearn to convert this grain object to the bnlearn formats. And so what we do to check to make sure are these equivalent? Do I have the same thing either way? I'm using all equal from base R. Is bn alarm, the same as grain to bn fit? So remember, I took this object, I converted it to grain, and then I'm converting grain back to the bnlearn format. And hey, did I lose something? Did I pick something up? Well, the difference is a difference occurs where it put in those uniform probabilities for us. And so that's when I have a bn fit. So if I have bn fit object in the bnlearn package, what happens is it actually works out all the probabilities for us. If I only have a bn object, what's going on there is I have the relationship between the nodes, but I don't have the actual parameters and the probabilities worked out. And that's the major difference. So here, when I check are these equal to each other? Yes, they are. Because here we're not concerned about the parameters, we're only concerned with the relationship between the variables. Now, something about the grain package is that we can set evidence to adjust our parameters, our models very easily. So if I set evidence, I can propagate throughout my model. I can change the conditional probabilities for each of the variables after I set a particular value. So here, I'm saying that the MVS variable is set to high. Well, once I know that, all of my conditional probabilities throughout the entire model change. Well, as is, if I set the evidence and then I pass that to bnlearn, even though I set the evidence, it's not going to update it. And so if I go through and I looked at how this was originally, this is the default state. It did not take advantage of that additional information. This is the original model before I knew what the MVS state was. Now, the help documentation says that you can set a parameter and it will actually update the model for you when you cross over to bnlearn. I could not get that to work. So I just cut that out and we don't talk about it at all. So I feel like the grain package format is a little bit better than bn fit because it fills in all the details. But if I want to use bnlearn, it doesn't really matter. I can go back and forth between them. All right, well, that's all I've got. This is some dense material. This is very specific to the code that we're working on. I hope that this is useful to you in the future if you end up using graphical models. Take care and stay safe.